In this video, we'll be looking at an example of continuity. Our first example of continuity is f of x equals x squared minus 4 at the value of x equals 2. So to determine whether or not a function is continuous at a very specific value, again, we're going to first start off by looking at the function. And on that function, we're going to evaluate at the given point. So we're going to go ahead and plug in 2 to this function. In this case, if I attempt to plug in 2, I get 4 minus 4, which is 0. And sure enough, f of 2 equals to 0. Now, just because it equals to 0 doesn't mean it's a problem. It just means that we end up getting a value of 0. There does exist a value for f of 2. The second detail of continuity, again, is does the limit exist? So the limit as x approaches 2 of this function x squared minus 4, what does that value equal to? And again, remember, if we remember how to evaluate limits, we either direct substitution, factor if we can't direct substitute, we could attempt to use conjugate or common denominators. Don't forget your trigonometric basic limits, as well as your infinite limits. So in this case, I'm going to go ahead and attempt to plug in 2. When I plug in 2, I end up with 0. So, is this function continuous at the point of x equals 2? And the answer is yes, because f of 2 equals to the limit as x approaches 2 of f of x. Again, this must be the conclusionary statement. Number 1, the function value exists. We plug the number into the function. Number 2, the limit value exists. If I go to plug in 2 here, does it give me back the exact same value? And sure enough, in both those cases, I get 0. So therefore, f of 2 equals the limit of as x approaches 2 of f of x, and therefore this function is continuous at the x value of 2. Again, we would say that f of x is continuous, and I'll abbreviate that as conti, at x equals 2. So the second example we're going to look at is this piecewise function right here. In this case, we're going to have to check at the value of negative 3. We're going to have to check it in such a way that we're looking at where it breaks. Again, this could be continuous, but it might not be. And the location of where it might not be is at the location where the function might not exist all the way through on the exact same function. So in this case, if we start off with f of negative 3, again, just simply plugging in negative 3, that's going to provide me with a value of negative 5, because again, when I go to plug in negative 3, I can't plug it in this one, but I can plug it in down here. When plugging in down here, I get negative 5. So that's my first step. It does exist. It has a value. That's part A. Part B, let me take the limit as x approaches negative 3 of f of x. Now, in terms of this value, I should be taking it on the limit based on where the function is behaving around negative 3. So I can't be working on this function here because that's where it is negative 3. I want to know what it's doing as we're getting closer and closer to that. Well, we're actually working on this function up here as x gets closer and closer to negative 3, just as long as it's not negative 3. So in that case, we'll be using this function. And if I try to plug in negative 3 right now, you'll notice that the top is 0 and the bottom is 0, and I can't plug in negative 3. Again, if I attempt to, this is undefined. This does not equal to anything. So what I'm going to do next is use my analytical evaluation of limit skills, and I'm going to factor that top piece, giving me x minus 4 and x plus 3. You'll notice then that I can cancel out what I like to call, again, that problem child, that x plus 3, giving me the limit as x approaches negative 3 of x minus 4, and when I plug in negative 3 now, I get a value of negative 7. So in this case, if I'm looking at this function right here, we can very clearly identify that part C fails. F of negative 3 does not equal to the limit as x approaches negative 3 of the function f of x. So by saying this, we can say that f of x is discontinuous at x equals negative 3. Now, with that statement being made, again, it comes from one of 3 possible details. The first detail, it might fail to be existent at the given point. Again, if we don't have this function value, it can't be continuous. The second detail it could fail with is if the limit value doesn't exist. In this case, the limit did exist. The problem is where this one failed is the fact that the two values, function and limit, don't actually equal to each other at that given point.